So yeah, hi everyone, my name is Lorenzo Maria, and today I will talk about my summer research project, that is airborne launch and recovery system, vision-based hook localization for autonomous recovery of an underwater vehicle. It is a really long title, and let's see what does this mean. First of all, what is this airborne launch and recovery system, or ALARS? It is a project, a joint project between Purdue University and KTH in Sweden, the university I'm from, and it is funded by Purdue, KTH, NSF, and SAR. It is a project about how to recover autonomously stuff from the sea. Stuff is not really a technical term. What we want to recover is our autonomous underwater vehicles like SAM. It is a device that Purdue and KTH have been developing for a couple of years now. And yeah, it is a device that can be used for underwater exploration, surveillance, water quality analysis, animal tracking, and it would be greatly beneficial for the logistic of these missions to be able to catch SAM from the sea, like to change its batteries if it's needed or for whatever reasons. So what happens in practice? Well, when a problem arises, SAM comes to the surface and it detaches a bomb. Then it pings like to the satellite that we need to to go and take it up from the sea. So we take a boat, we go near there, and our idea is to deploy a drone that can go around, find it, recover it through a winch rope hook system, and transport it back to the boat. There are numerous challenges involved in this kind of mission, like how to find SAM. GPS is not that accurate in open waters, so we need a way to somehow find it in the sea, in the ocean, how to catch it, and how to transport it back. Our summer focus was answering how to catch it. So how do we catch SAM? To answer this question, we need to solve three major sub-problems. The first one is finding the right spots for the hook to enter and exit the water, and by doing so, grappling SAM, like fishing it out of the water. Then we need the onboard computer to have some autonomous control for the drone movement and for the winch to decide for the length of the rope. And for all of this to make sense, we need to estimate the position of the hook at every time. Because if we know where the hook should go and we know how to make that happen, if we don't know where the hook is, it's really difficult to control. The whole pipeline kind of fails. And yeah, my research was about this estimation of the hook position. And we had two major tools for this analysis. The first one is ROS2, that is Robotics Operating System 2. It does basically what it says, so it lets us operate, communicate, and control robots in general, like SAM, like the drone, and this is what is called a TF3, and it gives us, it's also given by ROS2, and it gives us important informations like the relative positions of each element in the drone, and we can also get like the acceleration of the drone, its position, and we can control the rope length through it. If, the most important thing here in the end is the hook position, that is this thing over here, that we will use as the ground truth to validate our results. We compare this with a simulation environment like Unity, and so that we can get a scene and really simulate various missions to validate our results. We can see here a screenshot of our Unity simulation, where we have we can see the drone with our downward cameras and the winch that has the rope attached to it and controls the rope. We can see the red rope, and we can barely see the hook at the end of the rope. So, how do we estimate this hook position? First of all, we want to we want the drone to understand where the hook is in our camera feed. Then, through that, we want to calculate its three-dimensional position, and by adding the drone linear and angular acceleration, we want to track the hook even when the camera cannot really see it because it goes out of the field of view. So how does this work? Here we have the original camera feed from the cameras facing downward, and as you can see here we have Sam, here we have our rope, and here we have the hook that is at the end of the rope, and that's exactly where we want to go and say the onboard computer that's the hook at the end of the rope. How can we find it then? First of all, we can, since the rope is the only red thing in the scene, we can apply a color filter and take out the red, let it stand out. We can apply a grayscale, and through what are called canny edges, we can get the outline of the rope. Then we can calculate these so-called U-lines. We can see three of them here. They are the green ones, and through them it is, I won't go into detail on this, but it is pretty straightforward to find the hook. We also have other types of check that can assure us that we find the hook nearly every time, at least when it is visible. And yeah, we can see here a video of our Unity simulation. We can decide for the rope length. Here, the rope, we are changing it from 1 meter to 5 meters. And here we can see the original feedback and our hook detection. And even when we move the drone, we can see that we can always detect the hook on the camera. So, we now have X and Y in pixel. We have the position of the hook in the camera feed. We now need to calculate its three-dimensional position. How do we do it? Well, the thing is that we have an X and a Y, and that three-dimensional position is X, Y, and Z. So we need at least other information. And it becomes pretty straightforward doing so if we add the condition that the rope is taut. And it's not that heavy of a condition, that strong of a condition, because if we have a heavy enough hook, the rope will always, not always, but nearly always be taut, at least if there is not some great strange winds around. And I will go really fast on this, because really easy mathematics, but we don't have time to really see it that in depth. With the pixelated position, we can apply all the camera parameters, like this K matrix that is given by the camera resolution and its field of view, in order to get the line connecting the camera to the hook. However, we don't know where in this line the hook lies. That's exactly why we assume that the rope is taut. That way we can define the sphere around the sphere centered in the winch of radius, the rope length, and we can define a system between this line and the sphere to get our hook position estimation. We get, of course, two solutions to this system. One is upwards, but we only take the one with the negative z. And that should be it. However, we noticed that it's not that good. I mean, we get some kind of error here, and so we thought about adding another camera to the drone. So we had a second camera, and yeah, our idea was let's not use this sphere anymore, but just the intersection between these two lines. This is basically triangulation. And yeah, we don't get this point, we get that point. That is even worse. Why so? Well, it's because we have some errors in our hook detection of camera with the pixels. It's like watching the stars and say, yeah, like Polaris is nearly there. Well, nearly there is not enough because a millimeter error means like a billion kilometers error of their space. And here it's like that. I mean, the rope is 5 meters long. So even a small error in the pixel frame propagates and becomes really, really large in our map frame. So what do we do? Well, we can use the same trick as before. We can assume that the rope is out and find those two yellow points with both cameras. And we can average their results and project it back to the sphere. And yeah, the results should be better, and the results are better with these two cameras set up. And yeah, so now we have a three-dimensional estimation, and from there we would like to track the hook. I will not talk about about this. This is called Kalman filtering, and I will not talk about this for two reasons. First of all, it is an extremely difficult mathematical concept, in my opinion, and then it doesn't work as well as we would like it to. Yeah, we can see it in the results. Unfortunately, this Kalman filter doesn't work that well, but it works somehow. Yeah, we can see here the results for the single camera. The blue line is our ground truth. We want the red line, that is the estimation through the camera, and the green line, that is the Kalman filter, so the hook tracking. And we basically want the red line and the green line to be the most similar to, as similar to the blue line as possible. It doesn't seem that bad. We also calculated the mean square error. We have some error, but the only thing that I want to note here is that the Kalman filter doesn't give us a great, it's not really beneficial when we have the camera estimation, but when the cameras cannot see the hook because it goes out of view, we have a kind of a prediction of where the hook could be with the Kalman filter, so that's really good. We also have the double camera results, and I put those results in a table here. And yeah, this is basically the errors given by, I mean, the root mean square errors in the x, y, and z axis. And I mean, the smaller the error, the better the result. And we can see that double camera with slow movement, with a drone that moves slowly, gives us the best results. Okay, so what should you do? I mean, we should, there's a lot of work to do, and we would like to actual experiment, we would like to do an actual experiment with the real drone. We began it yesterday, and I decided to put this because we can see that we can really detect the hook. This thing over here. We can really detect our hook, this. As you can see in that picture over there. And we would also like to improve our Kalman filter in order to get that green line better. And we would also like to do some parameter analysis for the best camera positions and rotations. And yeah, that is all. Thank you for listening.
We have time for one or two questions. Anybody have any questions?
I have a small question about the ground truth.
Yeah.
What is the ground truth you use?
We get it from the TF3, and so like it's embedded in the system. I mean, in ROS 2 we added that the position of the hook in the TF3 so that in the simulation we can get the ground truth.
Okay.
Yeah. Okay.
But in simulation, the rope is straight or can be.
It's stout. It's always straight. Yeah. That's why it works. If it wasn't, of course we would have other issues. But we simulated as stout so that.
Yeah. Okay.
As we can see here, I mean, it is stout because this is pretty heavy. But yeah, that's what we would like.
Okay.
Yeah. Also in the real situation. Yes.
Do you have an idea to explain why the double camera but fast movement is pretty much the exact same as the single?
Well, that's why in our future work we would like a parameter analysis because right now the cameras are facing the same exact direction and so the field of view is not really expanded. We see nearly the same scene, so we have an improvement that comes from that thing that I saw with the projection of the sphere. However, a better result would come out when we decide, like, probably if we decide to have outward-looking cameras, so that we have a field of view that is bigger, we can see more what's happening, and so that the hook, even when it swings a lot, we can see it a lot more. So yeah, that's probably why.
Okay, good job.